So now we're on part B. In part B, we are asked to take this region R, and we're going to revolve it around the line y equals 7. In the earlier part of the video, we talked about how you would find the volume if you were taking a shape and you were revolving it around the x-axis. All you had to do, the volume in a situation like that, volume around the x-axis, was pi times your integral from your lower limit to your upper limit. You take your radius squared, you integrate that with respect to x. It's going to be the same big idea here, except things are going to work a little bit differently. We're not spinning it around the x-axis. We are taking the region and revolving it around the line y equals 7. Well, that region has a large radius. It's going to have y equals 2 square roots of x, generating the outer shell for that region. The radius for that large region, for any particular x value, if x is right here, the radius for that region will be determined by taking my top function, which is 7, subtracting from that the bottom curve, 2 times the square root of x, just like we did with area between two curves. But this expression, 7 minus 2 square roots of x, represents the large radius for, or that represents the radius for the outer shell of this volume of revolution. I can start my volume expression off. It's going to be pi. We are going from 0 to 9 still. And I'm going to take that large radius, which is 7 minus 2 square roots of x. We're going to square that, and we're going to integrate it with respect to x. If we do that, though, that would give us the volume for the red curve, y equals 2 square roots of x, being revolved around the line y equals 7. And that's great. That's a good start. But this is going to give us a volume that's too large. In order to fix that, what we're going to have to do is we're going to have to subtract off this piece here in the middle, this white shape. Well, this white shape is being revolved as well, and that actually gives you a smaller radius. If I revolve that white shape, maybe you want to think of it as a cylinder. The radius for that piece will be determined the same way as before. Top function minus bottom function, 7 minus 6. So the radius for this piece here, the part that we're going to scoop out, is 1 for every single x value. It's a constant. It doesn't depend on x. We're going to subtract that volume, which is pi, from 0 to 9. 7 minus 6, which is 1 squared, with respect to x. Since we're only being asked to write an integral expression, this is perfect. You are done. You can move on. You don't have to do anything else. For those of you that like fewer integrals rather than more, you could, if you'd like to. We have 2 integrals here. They're both being multiplied by pi, so that's going to be a factor that we could factor out if we need to. They're both starting at the same lower limit. They're both ending at the same upper limit. So you could, if you so desire, write it as one integral. We're going from 0 to 9, pi, 7 minus 2 square roots of x squared, minus 1 squared, or just 1, but I'll write it as 1 squared so we keep the square in there, and integrate that with respect to x. That is perfect. I wouldn't go any further than that. If you leave this as your answer, you get all the points. Leave that as your answer, you get all the points. Congratulations. I think we've just picked up another 3 points for our solution of part B. All right, so now we're on to part C. We had some technical difficulties during the filming of the video the other day, which is why now the wardrobe changed. A few days have gone by. But we're looking at region R. What we know is that the solid that we're talking about, the three-dimensional object, we're told that for each y, where y is between 0 and 6, the cross-sections of the solid, taken perpendicular to the y-axis, is a rectangle whose height is 3 times the length of the base in the region R. So the height is going to be 3 times the length of the base. We're going to write, but we don't actually have to evaluate the integral that gives us the volume. So let's back up on this for a little bit. We're told that our cross-sections are going to be taken perpendicular to the y-axis. Well, the y-axis goes this way, and if I'm going to be perpendicular, if my slices are perpendicular, I want to imagine I'm slicing the solid this way. And so the bottom of that slice will start on the y-axis and it will end on the curve y equals 2 square roots of x. We're going to have all of these little rectangles with bases on the region R. Now, each of those is going to have a length that is determined by finding the distance between the y-axis and the curve y equals 2 square roots of x. The one thing that's going to be a challenge for us is that when we're thinking about the distance, we're looking at the horizontal distance. The way I would find the horizontal distance for any of these points is I need to know the, for a fixed y, what the x-coordinate is here, what the x-coordinate is over here. And I'm going to be subtracting those two from one another. When we're doing problems where the volume, where your slices are going this way, our integral, instead of being an integral with respect to x, it is going to be an integral with respect to y. So our lower limit is going to be a y value, our upper limit will be a y value, our integrand is going to be in terms of y. So we're definitely going to be pushed with this problem a little bit. So let's get started. This function, this curve, can be written in another way. We know that y is equal to 2 square roots of x, but if I actually go through and if I solve that equation for x, I can divide both sides by 2. Y divided by 2 is the square root of x. I'm going to square both sides, and the result will be that y squared divided by 4 is equal to x. This is describing the same curve, but now I have it solved, I have it written in terms of x. That's going to be really important. So if I want to find the length, the distance between these 2 points, I'm going to start here on the y-axis. I'm going to go out this far. That x-coordinate is going to be defined by y squared over 4. So the length of these strips is y squared over 4. Now, depending on how comfortable you are with the visual, you want to remember that we're talking about slices coming this way. They're perpendicular to the y-axis. They are rectangles, and what's so special about the rectangles is that the rectangle, if that's the base, the height is supposed to be 3 times this base. So if this distance here is y squared divided by 4, the height, which is going to be coming out of the board, is 3 times that. To help visualize that, I'm going to redraw this, where this little line segment, y squared over 4, instead of imagining the rectangle coming out of the board, let's imagine the rectangle going up the board. This is the length of the base. The height of this rectangle, we are told, will be 3 times that, so 3y squared divided by 4. If I want to find the area of this rectangle, the area will be y squared over 4 times 3y squared over 4, which is 3y to the 4th divided by 16. That area is the area for one of these rectangles. Well, I need to add up all of those rectangles in order to get the volume of this 3-dimensional object. That's where the integral comes in. And I'll have the integral of 3y to the 4th over 16 dy. I'm integrating with respect to y, so I need to know the lower y value. I need to know the upper y value. We're going to be integrating from 0 to 6. If your calculus skills are strong, you could, of course, go through and integrate this. You could pull the 3 out front of the integral. It's a constant. Same thing with the 16. Use your general power rule to integrate. You'd evaluate the integral. You could do all of that, but we are told specifically in this problem just to set up the integral, don't evaluate it. So once you arrive at this answer here, you are done and you get to high-five your neighbor. Nice job. So let's move on to the next AP problem. All right, so this next problem that we're going to look at appeared on the 2009 AP exam. It was the 4th question on the exam, which means that it is a calculator inactive question. So let's put the calculators away and we're going to attack this problem armed only with our knowledge of calculus. So we have region R, which is bounded by the graph of the square root of x and x over 2, as we can see over there. Part A, we're going to be asked to find the area of R. We should be pretty comfortable with that. In part B, we're going to be told that region R is now the base of a solid. For this solid, the cross-sections perpendicular to the x-axis are squares. So we're going to be imagining our slices perpendicular to the x-axis. As we saw before, we'll draw the little base, and we'll imagine the shape that's formed that way. And then in part C, we're going to write, but we're not going to bother to evaluate, an integral that will give us the volume if r is rotated or about the horizontal line y is 2. So let's just jump right into this. And since this is our second video, we're going to go a little bit faster. I want to find the area of r. I'm going to do top minus bottom. So I need to start over here at the first intersection point, which is 0, 0. I'm going to stop at my second intersection point, which is 4, 2. We are going to do an integral with respect to x. The top function is given to us as the square root of x. The bottom function is x over 2. I want to integrate that with respect to x. I believe on the AP exam, 1 point was awarded for writing down this initial integral. And so if you're already able to do that, we're in a great place. Now we actually need to go through, need to do the integration. We're going to need to evaluate the function at the endpoints. In order to do that, I want to change my integrand into something that maybe is a little nicer, a little friendlier for us. So one of my first moves, I'm going to rewrite the square root of x as x to the 1/2. Additionally, I'm going to rewrite x over 2 as minus 1/2 x. I've now written both of these terms as powers of x. We're going to use the general power rule for integration, which says that the integral of x to the n dx is we add 1 to the power, and we divide by the new power. It's going to be plus c. This works unless n is equal to -1. That's when you get the natural log of the absolute value of x instead. So we're going to apply the general power rule down here. If I'm going to integrate x to the 1/2, I add 1 to the power, which gives me x to the 3/2. I'm going to divide by the new power, so 3/2, minus 1/2, integrate x. It already has an exponent of 1. We're going to get x squared over 2. I need to evaluate that function from 0 to 4. I can clean this up a little bit. X to the 3/2 divided by 3/2 is going to be the same thing as saying 2/3 x to the 3/2 minus 1/2 x squared over 2 is the same thing as minus 1/4 x squared. We're going to evaluate it between 0 and 4. To evaluate this function, we're going to plug in the top limit. We're going to get an answer. We're going to plug in the bottom limit. We're going to get an answer. Here it comes. We'll have 2/3 times 4 to the 3/2 power minus 1/4 times 4 squared. We've evaluated our integral at 4. Minus, we're going to evaluate our integral at 0. And depending on the expectations that have been set by your AP teacher, also depending on the section on the exam that you have to do a problem like this, it is fine for you to stop at this point. You have everything is a number. These are all numerical values. You don't have to simplify anymore if you don't want to, or if you're a little scared that you might make a mistake with the fractional exponents. But for the sake of completeness, we're going to go through this. We have 2/3, 4 raised to the 3/2 power. Back in Algebra 2, you were told that if I have a fractional exponent, the denominator tells you what root to take. So we'll take the square root of 4, which is 2. We'll cube that. We're going to get 8. Minus 1/4 times 16. From this, I'm going to subtract 2/3 times 0 to the 3/2, which is 0. Minus 1/4 times 0 squared, which is also 0. That works out nicely. 2/3 times 8 is going to give me 16 over 3. From that, I subtract 1/4 times 16, which is 4. I can then get a common denominator, 16 over 3 minus 4. We're going to get 16/3 minus 12/3 is equal to 4/3. That 4/3 represents the area bounded by these two functions, starting at 0, going all the way to 4, That's it. We're done. That was worth 3 points on the AP exam. Your first point for setting up your integral. The second point was for arriving at this part of the problem. The third point was for evaluating this function at those endpoints correctly. Again, you could have stopped here, you could have stopped here, you could have stopped here, you could stop anywhere along the way as long as they are all equal to 4/3. Let's move on to part B. All right, in part B, we're told that region R is the base of a solid, and for this solid, the cross-sections perpendicular to the x-axis are squares. So let's get ourselves oriented. Here's my x-axis. Slices are perpendicular to the x-axis, which means that the base of any one of these slices is going to look like that. It starts on the square root of x curve. It ends on x over 2. So if I want to find the length of any of these slices, it's going to be the square root of x minus x over 2. Like I did in the previous video, let's actually take this because technically the square is coming out of the board at you. And I'm going to redraw this so that we can see the square in a more natural way. This is the length of the base. Since it's a square, we know that the height is equal to the length. If I want to find that area, the area will be the square root of x minus x over 2 times the square root of x minus x over 2, so we can just get away with doing that squared. We are going to find the volume, so my volume will be found by doing the integral. Square root of x minus x over 2 squared dx. We're integrating with respect to x. We start at the first intersection point, which is 0. We end at the last intersection point, which is 4. And we might be happy to set this up. I think this gets you at least 1 point on the AP exam. But they do want us to find the true volume, which means we're going to have to integrate, we're going to have to perform the integration. We'll evaluate at the endpoints just like we did before. So let's get this ready for some calculus. I'm going to rewrite this as x to the 1/2 minus 1/2 x. I've got to square that whole expression. If I'm going to do that, I'm going to do the integral from 0 to 4, x to the 1/2 minus 1/2 x times x to the 1/2 minus 1/2 x with respect to x. I know if you're a Yes Prep student, if you came through our middle school, you're a big fan of doing the box for multiplication. So I'll set that up, x to the 1/2, negative 1/2 x, x to the 1/2, negative 1/2 x. X to the 1/2 times x to the 1/2 is x to the first power. X to the 1/2 times negative 1/2 x will give you negative 1/2 x to the 3/2 power. We'll do that again down here. Negative 1/2 x to the 3/2 power plus 1/4 x squared. That result, the area of this box, is actually how we're going to rewrite the integrand. We have x minus 1/2 x to the 3/2 power twice. So that would be the same as negative x to the 3/2 power plus 1/4 x squared. We're doing an integration with respect to x. All of these are powers of x. So all of these can be integrated using your power rule. Add 1 to the power, divide by the new power. Minus x to the 5/2. We add 1 to the power, divide by the new power. Plus 1/4, add 1 to the power, divide by the new power. Evaluate this function at the endpoints. We are almost done. The only thing left that you need to do in order to earn the full points on this question is evaluate this integral at 4, evaluate this integral at 0, and then stop. You get a little more board space. So if I do that, let's do this quickly. We're going to get 4 squared divided by 2 minus 4 to the 5/2 power divided by 5/2 plus 1/4 times 4 cubed over 3. All of that minus 0 squared over 2 minus 0 to the 5/2 over 5/2 power plus 1/4 times 0 cubed over 3. Again, I can stop here, and I would strongly encourage you to stop here. 4 squared is 16. 16 divided by 2 is 8. Minus 4 to the 5/2. Square root of 4 is 2. 2 to the 5th is 32. 32 divided by 5/2 is the same thing as 32 times 2/5. So we get 64 over 5. 4 cubed is 64. 64 thirds times 1/4 will give me 16 thirds. All of this minus 0 squared over 2, 0. 0 to the 5/2 over 5/2. 0. 1/4 times 0 cubed over 3, 0. My final answer I can leave as 8 minus 64 over 5 plus 16 over 3. And I'm done with all of that, or I can get a common denominator and reduce it to the fraction 8 over 15. My advice for you as a time saver on the AP exam, once you reach this step here, stop. Stop. The AP graders are perfectly satisfied with this answer. Every move you make after this, you are running the risk of losing a point, because maybe you will make a mistake with the exponents. Maybe you'll combine your fractions incorrectly. That is not a risk that you want to take. Secondly, this takes time. It takes time to go from this step over here to doing all my exponent work, all my fraction work. That is time better spent on another question later on in the test. So let's look at part C. Okay, so let's look at part C. In part C, we are asked to write, but do not evaluate, an integral for the volume of the solid generated when region R is rotated about the horizontal line y equals 2. So let's draw in the horizontal line y equals 2. That's the line that we're trying to rotate this shape about. We're going to take region R, and we want to imagine region R getting rotated about y equals 2, which means we are spinning it around y equals 2. That's our axis of rotation. We're going to have to do a subtraction of our integrals, because if I start at 2 and I go down to the bottom function, that's going to give me my large radius. I'm then going to have to subtract off this hollow shape, because remember, we're just taking R, region R, and revolving that around the line y equals 2. If I look at this large radius over here, which is going to be determined by finding 2 minus x over 2, that's how long this piece is. If I set my volume up as the volume equals pi, the integral from 0 to 4, 2 minus x over 2 squared dx, that volume will include this white area in here that I'm not interested in. So in order to remove that, we're going to scoop out, or we're going to subtract the region formed by this little section, which is 2 minus the square root of x. That's my small radius. So we're going to do another integral from pi, another integral from 0 to 4 times pi. And this will be 2 minus the square root of x squared dx. We're done. That is all that is being asked in this problem. Of course, if you like one integral versus 2, since both integrals start at 0, both integrals end at 4, I can do this with one integration. They're both being multiplied by pi, so I can write the pi in front. And then it'll be 2 minus x over 2 squared minus 2 minus the square root of x squared. Integrate all of that with respect to x, and we are done. We have completely solved 2 AP questions that I would not be surprised if something similar to this shows up on your AP exam on Wednesday, May 4th. Stay tuned for more videos.